Just 72 hours ago, the European Space Agency dropped what they boldly claimed was the closest ever view of 3 Atlas, the interstellar enigma that sparked both wonder and dread across the globe. With billions of dollars poured into state-of-the-art space technology and 7 Mars orbiters meticulously positioned for the ultimate cosmic photo op, expectations was sky high. But what did we get? A hazy white speck that could pass for a smudge on a dirty camera lens. Within minutes, social media ignited not with awe but with outrage. Amateur astronomers wielding modest backyard telescopes are capturing sharper images of comets millions of miles farther away, leaving the world questioning what went wrong. Meanwhile, NASA's Mars Reconnaissance Orbiter, armed with the most powerful camera ever sent to another planet, has gone inexplicably silent. The tired excuse of a government shutdown is starting to fray, especially when you consider that the Chinese and UAE orbiters are also conspicuously quiet. It's hard to ignore the growing sense of unease. As you read this, 3i Atlas is barreling toward a critical moment less than a week from slipping behind the sun, where it will be invisible to every telescope on Earth during what should be its most vibrant phase. The timing couldn't feel more suspicious. If Harvard physicist Avi Loeb's predictions hold true, what unfolds next could rewrite our understanding of what's possible in our cosmic backyard. This interstellar visitor might be more than just a rock hurtling through space. It could challenge the very foundations of our knowledge about the universe. Are we on the brink of a paradigm-shifting discovery, or is something being kept from us? If this mystery has you as captivated as it has me, hit that like button and subscribe to stay in the loop as this cosmic drama unfolds in real time. Drop a comment below. Tell me where you're tuning in, from what time it is there, and whether you think we're being told the full truth about 3 Atlas. Want to help spread the word? Share this on Facebook, Reddit, or your favorite messaging app. Your support keeps our community thriving. Thank you for always having our back. Chapter 1. The Photo Flop That Shattered the Internet. On October 7th and 8th, 2025, the space community held its breath only to let out a collective groan. 3 Atlas, the third confirmed interstellar object to grace our solar system, was skimming past Mars in a rare cosmic spectacle. For months, anticipation had been building to a fever pitch. 7 spacecraft from 4 space agencies were poised to snap groundbreaking images. Scientists teased clarity answers, perhaps even proof of what this mysterious visitor truly was. The hype was electric. Then the images dropped and the internet erupted. The European Space Agency's ExoMars Trace Gas Orbiter, positioned just 30 million kilometers from 3i Atlas during its closest approach on October 3rd, unveiled a series of images that were frankly a letdown. A blurry white speck drifting lazily across a star field. No detail, no structure. Nothing to hint whether this was a natural comet or something far stranger. The backlash was swift and brutal. Astronomy Vibes, a popular space commentary account on X, ignited the firestorm with a viral side-by-side comparison. One image showcased the crisp, dazzling detail of Comet Lemon, captured by an amateur astrophotographer with a modest, mirrorless camera. The other ASA's lackluster shot of 3 Atlas. The caption stung. If a mirrorless camera can nail Comet Lemon, why can't NASA capture 3 Atlas passing close to Mars? The post racked up over 40,000 reposts and counting. But it was the follow-up that hit hardest billions in funding. And this is the best photo they've got. Looks like a weather balloon in a foggy backyard. To grasp the fury, you have to understand the gap between what we were promised and what we got. The CASIS camera on the ExoMars Trace Gas Orbiter boasts an angular resolution of 11.36 microradians per pixel. At 30 million kilometers, that's roughly 340 kilometers per pixel. For context, 3IE Atlas's estimated nucleus spans 5 to 46 kilometers, meaning its entire solid core would barely fill a fraction of a single pixel. The ESA knew this from the start. Their cameras were built to photograph Mars's bright surface from a few hundred kilometers away, not faint objects tens of millions of kilometers distant. Nick Thomas, CASIS's principal investigator, admitted as much. This was a very challenging observation. The comet is 10,000 to 100,000 times fainter than our usual target. So why release images they knew would disappoint? Why fuel months of hype only to deliver a cosmic shrug? Officially, they claim they shared the best they had given the equipment's limits. But the timing feels calculated, a distraction, a placeholder to appease the masses. Because make no mistake, better images exist, far better, and they're being kept under wraps. Chapter 2. The Missing Crown Jewel. While the ESA's fuzzy images disappointed the world, NASA's Mars Reconnaissance Orbiter was silently poised to deliver a game-changer. Its high-rise camera, high-resolution imaging science experiment, is a marvel, the most powerful camera ever sent to another planet. From Mars's orbit, it can resolve objects as small as a kitchen table on the planet's surface. On October 3rd, as 3 Atlas swept closest to Mars, HiRISE's resolution was estimated at 30 kilometers per pixel. That's more than 10 times sharper than the ESA's lackluster shots. If 3A Atlas bore any unusual structure, any hint of something beyond a natural comet, HiRISE would have captured it with breathtaking clarity. Harvard physicist Avi Loeb, who's tracked 3 Atlas since its discovery, laid it bare in his October 7th blog post. The brightest pixel in the HiRISE image will provide the best constraint yet on the area of 3I Atlas. He urged NASA to release the images swiftly. It's now October 8th, and the silence is deafening. NASA's excuse: a US government shutdown. Over 15,000 employees, 80% of the agency's workforce, are furloughed. The agency's website is a ghost town, and public communications have ground to a halt. It's bureaucratic paralysis at the worst possible moment. But the explanation feels flimsy when you consider the broader picture. The ESA, a European agency immune to US political dysfunction, managed to release their images, however underwhelming. China's Tianwen-1 orbiter, equipped with a moderate-resolution imaging camera, had a clear shot at 3 Atlas. Yet they've shared nothing. The UAE's Hope orbiter, with its Emirates Exploration Imager, was also perfectly positioned. Still, not a single image has surfaced. Multiple space agencies, each with independent systems and priorities, are all holding back data on the most scientifically significant object to visit our solar system in years. The coincidence strains credulity. On X, speculation runs rampant, some suspect coordinated withholding. Others believe the images show something too sensitive for immediate release. The most fringe voices claim the images might reveal something so anomalous that public disclosure could spark panic. That theory sounds absurd until you look at what amateur astronomers are capturing. While professional agencies remain tight-lipped, backyard stargazers are sharing images that defy easy explanation, fueling questions no one seems eager to answer. Chapter 3. When amateurs see what professionals won't reveal. On October 3rd, as 3I Atlas grazed its closest approach to Mars, a Portuguese amateur astronomer known online as Dobsonian Power uploaded an image that set the internet ablaze. Armed with just a backyard solar telescope and bold digital enhancement, he captured what appeared to be an angular structure within 3I Atlas. Dark geometric shapes and protrusions that defied the comet's usual hazy glow. His caption was simple yet provocative. "What on earth is it?" Within 6 hours, the image ricocheted across astronomy forums, subreddits, and social media platforms. The reaction split the community in two. One camp saw undeniable proof of artificial structures, suggesting 3I Atlas was no ordinary comet. The other dismissed it as pareidolia, humanity's knack for seeing patterns in chaos exacerbated by processing artifacts from ill-suited equipment. The skeptics had a point. Solar telescopes built for the sun's blinding brilliance aren't designed for faint interstellar objects like 3I Atlas. Aggressive digital enhancement, they argued, was like sharpening a blurry photo until faces emerge from the noise, an algorithm inventing details that don't exist. But Dobsonian Power wasn't some fringe theorist wielding a cheap scope and wild imagination. A respected amateur astronomer with a decade of credible astrophotography, his YouTube channel meticulously documented his equipment methods and workflows. This wasn't a bid for clicks. When pressed about the strange structures in his 3I Atlas image, he didn't spin wild tales. Instead, he embraced uncertainty, promising to revisit the object in early November, when it reappears after passing behind the sun. His measured scientific caution only deepened the intrigue. Yet within 24 hours, a wave of articles flooded the web, each laser-focused on debunking his image. Headlines like "Amateur Telescope Captures Strange 3I Atlas Image, Here's Why It's Not." What it seems felt oddly synchronized, their tone defensive, as if rushing to smother the image's momentum before it could spark wider curiosity. Then came the enhancement wars. Across Reddit, Twitter, and conspiracy forums, users grabbed the original ESA images and ran them through their own processing tools. Some applied standard astronomical stacking techniques. Others leaned on AI upscaling tools built for low-resolution photos. A few unleashed chaotic machine learning models trained to conjure fine details from sparse data. The results were a kaleidoscope of contradictions. Some images revealed nothing but a sharper fuzzy dot. Others unveiled geometric patterns, edges, and structures too regular to be mere ice and rock. But heavy processing, especially with AI, muddies the truth. Feed an algorithm thousands of spacecraft images, and it might enhance a blurry dot into something suspiciously spacecraft-like, reflecting its training data rather than reality. It's a scientific dead end cloaked in false clarity. The flood of enhanced images had a curious side effect. It blurred the line between genuine observation and fabrication. Within 48 hours of the ESA's photo release, dozens of enhanced versions circulated online. Some depicted metallic surfaces, others hinted at solar panels, antennas, or even running lights and thrusters. Most were blatant digital art creations of Photoshop enthusiasts with too much time. But buried in the noise were a few images that felt different. Subtle, restrained. They showed just enough unusual regularity to make you pause and wonder, could something real be hiding amid the deluge of hoaxes? Chapter 4. The 4chan leak that refuses to fade. On October 4th, an anonymous user on 4chan's paranormal board dropped a bombshell titled simply ESA data leak. The post claimed insider knowledge about 3i Atlas, backed by a credential that felt chillingly plausible yet cloaked in anonymity. I am a doctoral researcher working with the European Space Agency with continuous access to the combined observational data of 3i Atlas. Internet leaks are often dismissed as fiction or trolling, but this one stood apart. Its technical depth was unnerving, avoiding sensational claims of alien invasions or secret missions in favor of cold specific anomalies that, if true, could rewrite what we know about 3i Atlas. The first anomaly, a chemical impossibility. The post alleged that spectroscopic analysis revealed 3i Atlas releasing roughly 100 kilga of nickel gas per second, yet with almost no ion emission. In cosmic chemistry, nickel and iron are inseparable, forged together in supernova explosions, traveling as twins through interstellar space and appearing side by side in comets and asteroids. Abundant nickel without iron is like smoke without fire, a violation of fundamental assumptions about natural cosmic matter. The second anomaly, a thermal contradiction. 3i Atlas spews gas and dust like an active comet heated by the sun, yet infrared observations show it remains inexplicably cold, far colder than its outgassing rate and proximity to solar radiation should allow. The poster likened it to someone sweating profusely in a freezer, a phenomenon where the physics simply don't align. The third anomaly, uncanny trajectory precision. Referencing public statements by Avi Loeb, the post noted 3i Atlas's orbital inclination of just 4.89 degrees relative to Earth's ecliptic plane, but it went further, claiming the object's path is a flawless, straight shot from the galactic core, no wobble, no deviation, no trace of gravitational nudges from nearby stars over its potential billion-year journey. It's as if it was aimed. Then came the chilling escalation. The poster described 3i Atlas as a post-biological entity, neither natural comet nor conventional spacecraft, but something in between. They claimed it operates with a 3-phase particle engine generating an estimated 75 megawatts, continuously transmitting an active signal. And in their words, probing our solar system. The post culminated in a theoretical bombshell. 3i Atlas might be a macroscopic quantum object, specifically a Q-ball, an exotic particle physics construct. A Q-ball, a non-topological soliton, could exist at scales far beyond subatomic, with properties defying conventional physics. It could be immensely dense, yet appear diffuse, instantly redistribute energy, to explain the thermal oddities and even favor specific isotopes, potentially accounting for the nickel without iron anomaly. Within 18 hours, screenshots of the post flooded Reddit, Twitter, and UFO research forums. A conspiracy subreddit thread racked up over 2,000 comments before moderators locked it for unverified claims. But silencing the thread didn't kill the conversation. It fractured into countless discussions across platforms. Some dissected the chemical anomalies, others latched onto the Q-ball hypothesis, and a few tied it to earlier speculations linking 3i Atlas to the 1977 WOW signal. The leak, like 3i Atlas itself, refused to be ignored, its implications rippling through the digital cosmos. Chapter 5. The 50,000 kilometers enigma. On October 4th, NASA's Perseverance rover, stationed in Jezero crater on Mars, captured a peculiar sight in the Martian night sky. Its right navigation camera revealed an elongated streak of light roughly 4 times longer than it was wide. At first, it seemed like a routine, long exposure shot of a moving object, nothing extraordinary. Comets and asteroids often appear smeared when a camera tracks the stars instead of the object itself. Standard stuff. But the math told a different story. When researchers calculated the streak's apparent size using Perseverance's known camera specifications and the distance to 3I Atlas at the time, the result was staggering 50,000 kilometers long. That's not a comet nucleus. It's not even a comet with a tail. It's something else entirely. For context, Earth's diameter is a mere 13,000 kilometers. If this streak reflected the true physical size of 3I Atlas, we were staring at an object nearly 4 times wider than our planet. Social media erupted with theories. Was 3I Atlas a colossal cylindrical craft, its true form hidden behind a veil of gas and dust? The timing only fueled the speculation. This image surfaced just 1 day after the Mars flyby, when space agencies worldwide fell eerily silent. Some saw it as evidence of something profoundly anomalous, something that defied easy explanation. The buzz grew so intense that Representative Annapolina Luna, a congresswoman known for her fascination with unexplained aerial phenomena, reached out directly to Harvard physicist Avi Loeb for answers. Pause and consider that a sitting U.S. representative felt compelled to bypass NASA's usual channels to consult a renowned scientist about a Martian photograph. That's not standard procedure. It hints at serious concern within official circles, enough to seek expertise outside the typical pipeline. Loeb's analysis was meticulous and on the surface reassuring. He calculated that Perseverance's navigation camera has an angular resolution of 0.33 milliradians per pixel. At the roughly 38 million kilometer distance to 3A Atlas, when the image was taken, that translates to about 12,500 kilometers per pixel. The streak spanning 4 pixels yielded the 50,000 kilometer length. But Loeb argued this was an artifact of composite imaging. The streak didn't show 3I Atlas's actual size. It traced the object's path across the Martian sky during a long exposure, likely 10 minutes of stacked images. His logic was airtight. Mars orbits the Sun at 24 kilometers s, while 3I Atlas moved at 67 kilometers in the opposite direction, creating a relative velocity exceeding 90 kilometers. Over 10 minutes, that's 54,000 kilometers of travel, almost exactly the streak's length. The shape wasn't the object itself, but its motion smeared across time. Case closed, right? The cylinder theory debunked by straightforward physics. Yet Loeb included one sentence that conspiracy theorists seized like a lifeline. If the NavCam images represent single snapshots with an exposure time below 3.2 seconds, then the brightness and angular length of the observed source imply that it is not 3I Atlas. In that scenario, the source might be much closer to the camera, capable of appearing elongated with a smaller spatial size and slower speed. In other words, if these were single-frame captures, Perseverance didn't photograph 3I Atlas at all. It captured something else, something closer to Mars. That single qualifier cracked open a door no clarification could fully shut. NASA has remained silent on whether the image is a composite or a single frame. No metadata has been released. No exposure time or stack details have been provided. The government shutdown excuse surfaces here too. No staff to process requests. No one to confirm basic technical details about the image's capture. The mystery lingers unresolved as questions multiply in the void of answers. Chapter 6. 48 Years of Silence. On August 15, 1977, Ohio State University's Big Ear radio telescope captured a 72-second burst of radio energy so extraordinary, so precisely structured, that astronomer Jerry Eman circled it on the printout and scrawled one word in red ink: "Wow." For nearly 5 decades, this signal has stood as one of the greatest enigmas in the search for extraterrestrial intelligence. Originating from the direction of Sagittarius near its densest star fields, it was narrowband, locked onto a single frequency, and it has never repeated. Hundreds of follow-up observations, thousands of hours of listening to that same patch of sky, nothing. Just that singular burst, 48 years ago, followed by an unrelenting cosmic silence. Then Avi Loeb ran the numbers on 3i Atlas. He calculated its position on August 12, 1977, just 3 days before the WOW signal was detected, approximately 600 astronomical units from Earth, 600 times the distance between Earth and the Sun. More crucially, he determined the direction 3i Atlas was approaching from at the time right ascension. 19 hours, 40 minutes, declination plus 119 dig. The WOW signal originated at right ascension, 19 hours, 25 minutes, declination 27 dig. The two directions are separated by roughly 9 degrees. In the vast expanse of space where objects could arrive from any direction, the odds of this alignment are a mere 0.6%. Not impossible, but strikingly suspicious. Loeb didn't stop there. He posed the next logical question: if 3i Atlas sent the WOW signal from 600 AU away, how powerful would its transmitter need to be? The math is clear. The signal's detected intensity ranged between 54 and 212 Jansky across a 10 kHz bandwidth. At 600 AU, that implies a transmitter outputting between 0.5 and 2 gigawatts, comparable to a terrestrial nuclear power plant focusing its energy into a tight radio beam. For an advanced civilization, this is entirely plausible, especially for a signal meant to cross interstellar distances without wasting energy on omnidirectional broadcasting. Another detail sharpens the intrigue. The WOW signal was detected at 1:420.45564556 MHz, blue shifted by about 10 km toward Earth, relative to the hydrogen line, suggesting the source was moving toward us. 3i Atlas is currently approaching the Sun at 60 km. Loeb posits that if this object has maneuvering capabilities, it could have been traveling slower in 1970, perhaps accelerating later after detecting habitable zone planets in our solar system. Could the signal have been a reconnaissance pulse, a radar scan, probing for signs of a technological civilization before committing to a closer approach? The frustration lies in how simple it would be to test this hypothesis. Point a radio telescope at 3i Atlas, tuned to the hydrogen line frequency. If it's transmitting, we'd know within hours. If it's silent, the WOW signal connection is likely coincidental. A straightforward experiment, a definitive answer. Yet, as Loeb noted in his latest blog post, not a single radio telescope has reported data on 3i Atlas. The very large array hasn't looked. Arecibo lies in ruins. Green Bank has published no observations. Even SETI, an organization devoted to finding extraterrestrial signals, has announced no public monitoring efforts. The silence from the radio astronomy community is as deafening as the cosmos itself. Chapter 7. The Path That Shouldn't Exist. Picture this: you're blindfolded, standing across a room, and you hurl a dart at a spinning globe. Not only does it hit the globe, but it lands within a whisper of the equator. That's the kind of jaw-dropping improbability we're grappling with. when we examine how Third Atlas entered our solar system. Interstellar objects can streak in from any corner of the cosmos, their paths scattered across the celestial sphere like stars in a chaotic sky. They should arrive at every conceivable angle with no preference for direction. Yet 3D Atlas slipped into our solar system with an orbital inclination of just 4.89 degrees relative to Earth's ecliptic plane less than 5 degrees. That's a needle in a cosmic haystack landing in under 1% of all possible arrival angles. Avi Loeb has been relentless pounding this point in every interview, blog post, and public statement since July. This trajectory isn't just unusual. It's statistically staggering, a profound anomaly for a random interstellar object. To grasp why, consider how objects dance through the galaxy. Stars in the Milky Way's disk orbit the galactic center with a shared rhythm, but they also jiggle in random motions up, down, side to side like bees buzzing around a hive. This randomness means that objects ejected from distant star systems should barrel toward our solar system from any direction with no bias toward any particular path. There's no cosmic highway steering interstellar visitors neatly into our ecliptic plane. And before you wonder if objects from the Milky Way's disk naturally slide in at shallow angles, Loeb's already debunked that. The galactic disk itself tilts at about 60 degrees relative to our solar system's ecliptic plane, more than 10 times the inclination of Third Atlas. If this object came from a typical star system in the galactic disk and was flung out randomly, it should have arrived at a steep angle, not this eerily precise, shallow one. The alignment defies what galactic geometry predicts. Now compare Third Atlas to the only other interstellar objects we've spotted. Oumuamua, discovered in 2017, came careening in with an inclination of 123 degrees and wildly tilted, plunging from above the solar system's plane. Tuai Borisov, spotted in 2019, arrived at 44 degrees, still steep, still fitting the mold of a random interstellar visitor. Both behaved as expected, like cosmic drifters following no particular rule. But Third Atlas, it's the renegade, the outlier that breaks the pattern. Loeb crunched the numbers. Assuming random arrival directions, the chance of this alignment is less than 1%. Some colleagues pushed back, arguing his statistics might be too conservative. Suppose the true probability of Third Atlas's razor-sharp trajectory is closer to 5 or 10% when you factor in selection effects and observational biases. Fair enough. Even at 10%, you're still staring at a cosmic rarity, something that should only happen once in every 10 interstellar objects we detect. And we've only seen 3. The odds of the third being this freakish exception rather than the norm tilt heavily against mere chance. Now, pile on the rest. The WOW signal alignment. Less than a 1% probability. Chemical quirks showing nickel but no iron unheard of. Thermal properties that contradict themselves. Baffling. The absence of high-resolution images from multiple space agencies suspicious. A government shutdown hitting precisely when NASA's needed most uncanny. Any one of these could be brushed off coincidence, measurement error, or bureaucratic bumbling. But stack these anomalies, multiply those tiny probabilities, and the combined improbability becomes a towering wall impossible to ignore. There's a statistical trap called the prosecutor's fallacy, where people mistake a cluster of rare independent events for a grand conspiracy when they're just random flukes aligning by chance. Flip a coin enough times, and you'll eventually get 10 heads in a row. It doesn't mean the coin's rigged. It just means you flipped it enough. Skeptics will claim that's what's happening with 30 Atlas, a natural comet with a handful of odd but explainable traits that just happened to show up together. Unlikely. Sure. Impossible? No. But there's a flip side. If something walks like a duck quacks, like a duck swims like a duck, and has duck DNA at some point, you've got to entertain the idea it's a duck. When an object screams in on a statistically improbable path, flaunts chemical signatures that defy natural processes, echoes a 48-year-old unexplained radio signal, and triggers governments to clam up on their best imaging data. Maybe it's not just a random chunk of ice and rock from another star system. Chapter 8. When questions turn dangerous. Around October 5th, something peculiar began to unfold. Across various platforms, users reported their posts about 33 Atlas vanishing into thin air. These weren't flagged as misinformation or removed with a warning they simply ceased to exist. A Reddit user shared a meticulous thread dissecting chemical anomalies from an alleged ESA leak. Within 2 hours, it amassed hundreds of upvotes and a flurry of comments. Then poof, it was gone. No moderator explanation, no trace of deletion. When the user tried reposting, the submission was silently blocked, shadow banned without a whisper of notice or reason. On Twitter now, X, a similar pattern emerged. Astronomy Vibes, an account that skyrocketed to fame for questioning the ESA's photos, saw its engagement plummet after October 7th. Posts that once reached tens of thousands were suddenly capped at a few hundred views. No official restrictions, no warning messages, just a subtle, deniable algorithmic chokehold. Quiet, yet ruthlessly effective. Other voices in the space astronomy community echoed the same eerie experience. Videos about 30 Atlas, which typically thrived, were now languishing with a fraction of their usual audience. YouTube presented its own chilling twist. Creators posting speculative analyses of 30 Atlas started receiving demonetization notices. The reasons were vague and varied. Some videos were flagged for discussing sensitive topics without sufficient context. Others were labeled as potentially misleading scientific content. A few were slapped with the cryptic charge of being unsuitable for all advertisers. The pattern was unmistakable. Videos proclaiming 33 Atlas as just a comet neatly aligned with mainstream science, those sailed through, monetized and promoted. But dare to suggest anomalies worth exploring, and your content became an advertiser's pariah. Facebook took the most brazen approach. Its third-party fact-checking system began aggressively targeting 33 Atlas content. Posts sharing the 4chan leak were hit with missing context warnings. Discussions of trajectory anomalies, even those directly quoting Avi Loeb's published calculations, were branded partly false. The fact-check articles oozed reassurance space agencies confirm no threat from interstellar comet. Experts say unusual features are likely natural processes. The message was clear: don't question, don't speculate, trust the authorities, and move on. The timing felt orchestrated. This crackdown surged within 48 hours of the ESA photo release, just as public frustration over the lack of clear images reached a fever pitch. It was the kind of pattern that made conspiracy theorists feel validated, and skeptics dismiss it as paranoid overreach. After all, social media platforms suppress content, daily algorithms shift engagement, ebbs, fact-checkers flag misinformation. It's standard procedure. But when it all converges on one topic at the exact moment, public curiosity peaks and official answers are scarce. It starts to look like more than coincidence. Some creators adapted weaving coded language to dodge the suppression. Instead of Theta Atlas, they'd say the visitor or the object. Words like alien or extraterrestrial became non-terrestrial or anomalous. It was as if a new lexicon was born to discuss what the platform seemed determined to silence. The Streisand effect kicked into overdrive. The more content was stifled, the more people suspected there was something worth hiding. The harder fact-checkers pushed back, the less trust the public had in the official narrative. Every attempt to control the conversation only fueled the belief that the conversation needed controlling. Chapter 9. The moment we can't watch October 29th and 30th. Mark those dates. In less than 72 hours from now, 3I Atlas will reach perihelion, its closest approach to the Sun. It will pass at a distance of approximately 202 million kilometers, just inside the orbit of Mars. For a natural comet, this is the moment of truth. The intense solar radiation at that distance should cause dramatic outgassing, possibly even fragmentation. We've seen it happen before. Comets get close to the Sun, the heat becomes too much, and they break apart into pieces. Spectacular when it happens. And if 3I Atlas is just an ordinary chunk of ice and rock from another star system, that's exactly what should occur. But here's the problem. We won't be able to see it. 3 Atlas will be on the opposite side of the Sun from Earth during its perihelion passage. Every ground-based telescope on our planet will be useless. The object will be lost in the solar glare, completely hidden from observation during what should be its most active and revealing moment. Some are calling it unfortunate timing. Others see it as suspiciously convenient. If you wanted to do something without being watched, you couldn't pick a better window. Avibe has been explicit about what happens next. In his October 3rd blog post, published on the day of the Mars flyby, he laid out 2 scenarios. If 3 Atlas is a natural comet, it may erupt in a flare of outgassing or break up into icy fragments soon. The sunlight will deposit gigawatt of power onto its surface. That energy has to go somewhere. For ice and rock, it goes into vaporization, sublimation, possibly structural failure. But then Lowe added the alternative. Alternatively, if it is technological, it may maneuver to benefit from the Sun's gravitational assist or release probes that could intercept the Earth or other planets owing to its retrograde orbit opposite, in direction to the motion of the planets around the Sun. Read that again. Release probes that could intercept Earth. He's not talking about passive observation anymore. He's talking about active deployment. The retrograde orbit is key here. 3 Atlas is moving opposite to the direction planets orbit the Sun. That means any probe it releases doesn't have to fight against planetary motion to reach us. It can simply drop into an intercept trajectory and let orbital mechanics do the work. From behind the Sun, hidden from our view, it would be trivial to launch something towards Earth that wouldn't be detected until it was already close. Lowe went further. He wrote, "When you look at the Sun in the coming weeks, keep in mind that 3 Atlas is passing behind it. If 3 Atlas will maneuver towards Earth when it reappears on the other side of the Sun, the financial markets may crash. Financial markets may crash." That's not metaphor. That's not hyperbole. He's suggesting that if this object demonstrates technological capability, if it alters course toward Earth after perihelion, the economic and social consequences would be immediate and severe. Stock markets respond to uncertainty. The uncertainty of a potentially hostile interstellar object actively changing its trajectory toward our planet would be existential level uncertainty. The timing of everything compounds the tension. The government shutdown means NASA is offline during the critical observation window. The best images from the Mars flyby are still unreleased. Amateur astronomers can't observe the object for the next month because it's behind the sun. Radio telescopes haven't checked for transmissions as 30 Atlas hurtles toward its perihelion on October 29th and 30th. We're careening into the most pivotal moment of this cosmic encounter with our eyes wide shut. Whether by sheer incompetence or calculated design, we've stumbled into a scenario where the world's telescopes will be useless, blinded by the sun's glare. We won't know what 32 Atlas does at its closest approach to the sun, its moment of truth, until it's already happened. The object could erupt in a dazzling display of cometary outgassing fracture into glittering fragments. Or if it's something more, execute maneuvers that could reshape our understanding of the universe. And we'll be none the wiser until it emerges from the sun's shadow. But one group is refusing to sit idly by. The Galileo project, spearheaded by Avi Loeb himself, is our last line of sight. Operating 3 observatories, one in Massachusetts, one in Pennsylvania, and one in Nevada. This initiative was built to hunt for anomalous phenomena in our skies. These aren't your average backyard telescopes. Each observatory bristles with high-resolution cameras, infrared sensors, and radio receivers meticulously designed to detect anything out of the ordinary, from unexplained aerial objects to potential signals from beyond. During late October and early November, as 32 Atlas sweeps behind the sun, all 3 facilities will shift into overdrive, scanning the heavens for any hint of unusual activity. The stakes couldn't be higher. If 33 Atlas is technological, as Loeb has dared to suggest, and if it releases probes during its perihelion passage, probes that could exploit its retrograde orbit to target Earth, the Galileo project's instruments might be our only shot at catching it. If there's a surge in unidentified aerial phenomena, UAP activity tied to this moment, their sensors could pick up the faint glint of a probe, the whisper of a radio signal, or the heat signature of something defying known physics. But here's the sobering reality: might is the operative word. 3 observatories, no matter how advanced, can only cover a sliver of Earth's vast sky. If something comes, whether a probe or something stranger, and it slips outside those narrow observation zones, it could pass undetected, a silent visitor in the night. The Galileo project's efforts are a flicker of hope in an otherwise darkened vigil. While the world's major observatories are sidelined and NASA remains offline amid a government shutdown, Loeb's team stands as a lone sentinel. But their reach is limited, their field of view a mere fraction of the heavens. If 33 Atlas makes its move behind the sun's veil, deploying probes or altering its course, the window for detection is razor thin. We're left to grapple with an unsettling truth. The most critical moment of this interstellar encounter is unfolding in a blind spot, and our ability to see what's coming hangs by the slimmest of threads. Chapter 10. What lies beyond the sun's veil. Come early November, the cosmic curtain will part. The Atlas will emerge from the sun's blinding glare, once again visible to Earth's ground-based telescopes. After months of speculation, debate, and unanswered questions, we'll finally have a chance to see what survived its fiery perihelion passage on October 29th and 30th. Telescopes will lock onto its path, scrutinizing whether it endured the sun's relentless heat intact or shattered into fragments under solar stress. We'll measure its trajectory with precision, searching for any hint of course corrections that defy natural explanation. This is the moment when the past 4 months of fevered theories, ranging from plausible scientific inquiries to wild conspiracies, will either be validated or dismissed as collective hysteria over a mundane interstellar visitor. If 30 Atlas reappears on the same hyperbolic trajectory, it entered our solar system with showing clear signs of fragmentation or heightened outgassing consistent with solar heating, the mystery may dissolve. If it behaves like 2I Borisov, the interstellar comet that passed through in 2019 with its predictable sublimation and icy outbursts, the case will be closed. It would be a natural comet perhaps, with unusual chemistry or a statistically improbable trajectory, but ultimately just a frozen relic from another star system passing through ours without fanfare. The supposed connection to the WOW signal would be chalked up to coincidence. The 4chan leak would fade into the realm of creative fiction. The missing NASA images would be explained away as bureaucratic delays during a government shutdown. Everything would snap back into a comforting framework. Interstellar objects are fascinating, but not alarming, a curiosity rather than a crisis. But what if it doesn't? What if 30 Atlas emerges with an altered trajectory, showing subtle course corrections that can't be attributed to the erratic thrust of outgassing? What if radio telescopes finally trained on the object pick up structured transmissions patterns that defy natural phenomena? What if, when the NASA images eventually surface, they reveal geometric structures or anomalies that no comet should possess? If any of these possibilities come to pass, we'll find ourselves in uncharted territory, not just scientifically, but socially, politically, and economically. Every assumption about humanity's place in the cosmos would be upended. Governments would face an immediate test. How do you respond to evidence of extraterrestrial contact in real time with the world watching? The implications would ripple far beyond observatories, shaking the foundations of global markets, belief systems, and societal stability. Avi Loeb, ever the provocateur, has introduced a framework to navigate this uncertainty, the Loeb scale. It's a ranking system designed to assess an object's likelihood of artificial origin and its potential threat level. Rank 1 signifies an object almost certainly natural, with anomalies that are intriguing but explainable. Rank 10 denotes something unequivocally artificial, demonstrating hostile intent and the capability to reach Earth. Loeb has publicly stated he won't rank 30 Atlas lower than a 2. Even in the best-case scenario, the object's anomalies, its chemistry, trajectory, and behavior are too persistent, too numerous, and too correlated to dismiss outright. A rank 2 means it's probably natural but carries enough unexplained quirks to demand rigorous investigation. It means we can't rule out an artificial origin without more data. That's where we stand now, teetering between a probable cosmic rock and a possible technological artifact, suspended in a state of uneasy anticipation. November will bring our first chance for answers, but they won't come quickly. The European Space Agency's Jupiter Icy Moons Explorer JUICE spacecraft is set to observe THRO-3 Atlas between November 2nd and 25th, using an array of instruments to capture the object in its post-perihelion state, when it should be at its most active. But the data won't reach us until February 2026, delayed by communication lags and processing time. 7 months of waiting for images and measurements taken in November. 7 months of wondering whether JUICE's observations will reveal routine cometary outgassing or something far stranger. 7 months of questioning whether the fuzzy, underwhelming image the ESA released in October was truly their best effort, or a carefully curated placeholder to manage a revelation they're not ready to deliver. Whatever THRO-3 Atlas turns out to be its journey has already exposed a deeper truth about our civilization. The public's response, rife with skepticism, distrust, and conspiracy, reveals a profound lack of faith in our institutions. Official reassurances ring hollow. The timing of government shutdowns, missing NASA images, and delayed data releases feels too convenient for many, whether those patterns are real or imagined. We're prime for suspicion because history has taught us, sometimes painfully, that what starts as conspiracy theory can later emerge as confirmed fact. The conversation around THRO-3 Atlas has become a mirror reflecting our collective unease, our hunger for truth, and our fear that we're not ready for what might come next. As we wait for November, for the telescopes to turn skyward, and for JUICE's distant gaze to return, we're left with one haunting question. Will THRO-3 Atlas sail out of our solar system as a fleeting curiosity? Or will it force us to confront a reality we've only dared to imagine? Chapter 11. The Invisible Visitor. On October the 1st, 2025, a cosmic phantom the size of a giraffe slipped silently through the narrow gap between Earth and our orbiting satellites, passing closer to our planet than the International Space Station's orbit, a mere 400 kilometers above our heads. Asteroid 2025 TF, a fleeting interloper from the depths of space, came and went without a single alarm raised. By the time astronomers caught a fleeting glimpse of it, the rock had already vanished, retreating into the inky blackness of the cosmos, like a shadow that never bothered to announce its presence. Stop and consider the weight of that for a moment. We live in an age of extraordinary technological prowess, where telescopes can capture the faint glow of galaxies forming billions of years ago, peering into the universe's earliest chapters with breathtaking clarity. Yet, a chunk of space debris close enough to practically skim our atmosphere evaded every detection system we have until it was already fading into our cosmic rearview mirror. This revelation is equal parts humbling and unnerving. It's a reminder of how much remains unseen in the vast theater of the night sky. Even as we congratulate ourselves on our scientific triumphs, if this cosmic close call stirs the same mix of awe and unease in you as it does in me, drop a comment below. Tell me where you're reading from, what time it is there, and whether you're more alarmed or captivated by the fact that we're still so blind to what's passing by. Are we missing harmless pebbles or something far more significant? If you're as fascinated by these celestial mysteries as I am, share this story on X, Facebook, Reddit, or your favorite messaging app to keep the conversation alive. Your support fuels our collective curiosity about the wonders and risks lurking above. Asteroid 2025 TF was small, measuring between 1 and 3 meters wide, a cosmic speck that, had it plunged into our atmosphere, would have erupted into a brilliant fireball, incinerating itself in a spectacular but harmless display. It posed no threat to cities, ecosystems, or civilizations. But its undetected flyby carries a far weightier message, one that haunts astronomers and keeps them staring at the stars long into the night. If we can't spot an object this close, hurtling at speeds that could traverse the distance from New York to Los Angeles in less than a minute, what else are we missing? The European Space Agency and NASA maintain vigilant watch over thousands of near-Earth objects, meticulously cataloging those classified as potentially hazardous asteroids, at least 140 meters in diameter, that pass within 7.5 million kilometers of Earth, roughly 20 times the distance to the Moon. By those standards, 2025 TF was a negligible blip, far too small to warrant priority. Our telescopes and survey systems are calibrated to hunt the giants, the civilization enders, the catastrophic behemoths, capable of unleashing extinction-level devastation if they strike at the wrong angle. But this tiny visitor exposes a glaring blind spot in our cosmic defenses. Space is not a serene, empty void. It's a turbulent sea of debris teeming with relics from the solar system's chaotic birth. These are fragments of ancient collisions, shards of worlds that never fully formed, and remnants of primordial chaos from when Earth was still a molten cauldron. Most of this material stays safely distant, locked in stable orbits within the asteroid belt between Mars and Jupiter, or drifting in the frigid expanse of the Kuiper Belt beyond Neptune. Yet the cosmos is a restless place, governed by subtle but relentless forces. A gravitational tug from Jupiter's immense mass, a nudge from a passing comet, or the faint ripple of orbital resonance can destabilize these paths, flinging rocks onto new trajectories that sometimes intersect with Earth's. 2025 TF's stealthy approach underscores how vulnerable we are to these unpredictable wanderers, even the small ones that slip through the cracks. What makes 2025 TF's flyby particularly striking is its timing, arriving in a month already charged with celestial drama. October 2025 has been a whirlwind of cosmic activity, with the 3D Atlas commanding global attention as it races toward its enigmatic perihelion behind the Sun. The skies feel alive, almost conspiratorial, as if the universe is orchestrating a performance we're only half equipped to witness. This tiny asteroid's undetected dash past Earth raises a chilling question in a month already electric with intrigue. What else might be gliding through the darkness, unseen and unannounced? Could there be other visitors, natural or otherwise, slipping past our gaze while we're fixated on the looming mystery of 30 Atlas? The invisible visitor has left us with a humbling truth. For all our telescopes and technology, the cosmos still holds secrets. It's not ready to share, and we're left wondering what else might be out there waiting to surprise us. Chapter 12. The Brightening Wanderer. A cosmic voyager steals the spotlight as it streaks across our October skies. Comet C2025. A6, affectionately dubbed Lemon after the observatory that first spotted it, is dazzling stargazers worldwide. Unlike a sneaky asteroid that slipped by unnoticed, Lemon is making a grand entrance, growing brighter each night as it nears Earth. Astrophotographers are capturing its brilliance, a glowing orb of ancient ice and dust, trailing a ghostly tail across the heavens. Carefully tracked since its discovery, Lemon now hovers on the cusp of naked eye visibility. In the coming weeks, under dark, clear skies, you might catch it yourself, a faint smear of light with a shimmering tail stretching away from the sun. Unlike asteroids, rocky or metallic relics forged in the solar system's warmer inner regions, comets like Lemon are icy wanderers born in the frigid outer reaches. Often called dirty snowballs, this nickname barely captures their cosmic allure. A comet's nucleus is a frozen trove of water, carbon dioxide, methane, and ammonia mingled with dust and organic compounds, the chemical seeds of life. As Lemon nears the sun, solar heat transforms its icy surface, sublimating solids directly into gas. This process births the coma, a vast, glowing shroud of gas and dust stretching hundreds of thousands of kilometers. Solar wind and radiation sculpt this material into a radiant tail, always pointing away from the sun, no matter the comet's path. Lemon isn't alone in October's cosmic parade. Another visitor, C2025R2, nicknamed Swan, glides past Earth later this month at a mere 0.26 astronomical units, close enough to dazzle through binoculars or small telescopes. Both comets currently glow at magnitude 6, teetering on the edge of human sight in pristine conditions. Yet comets are wild and unpredictable. A sudden spin might expose fresh ice to sunlight, sparking a brilliant flare, or an outburst could hurl plumes of material into space. Some even shatter under solar heat or tidal forces, each fragment forming its own coma and tail. Beyond their beauty, comets captivate us with their link to deep time. Their ice formed billions of years ago in the solar system's frozen fringes predates Earth's oceans, the moon's final form, and the first stirrings of life in ancient tidal pools or deep-sea vents. Some scientists propose that comets like Lemon delivered water to early Earth, fueling our oceans during a cosmic barrage. Others suggest their organic cargo amino acids, the building blocks of proteins, seeded the raw materials for life. This profound connection between ancient comets and life's origins prompts scientists to wonder, how common are these ingredients across the universe? Chapter 13. A Nursery for Moons. In the vast cosmic expanse, 625 light-years from Earth, a breathtaking drama is unfolding, captured by the piercing gaze of the James Webb Space Telescope. For the first time, astronomers have directly observed a moon-forming disk, a mesmerizing rotating ring of gas and dust encircling an exoplanet, known as CTB. Within this celestial whirlpool, Webb has detected a vibrant chemical symphony: hydrogen cyanide, acetylene benzene, propyne ethane, and carbon dioxide, carbon-rich molecules that resonate with the ancient origins of our own solar system. These are the building blocks of moons, and their presence offers an unprecedented window into a process long theorized but never witnessed until now. The scene evokes the birth of Jupiter's Galilean moons, Io, Europa, Ganymede, and Callisto, first glimpsed by Galileo in 1610 through his rudimentary telescope. These moons, orbiting in a precise flat plane around Jupiter, are believed to have coalesced billions of years ago from a disk of gas and dust encircling the gas giant, much as the planets formed from the primordial disk around our young sun. Ganymede and Callisto, composed of roughly 50% water ice with rocky cores of carbon or silicon beneath their frozen exteriors, stand as enduring evidence of such a circumplanetary disk. In CTB's disk, we see a parallel process unfolding, a cosmic nursery, where the raw materials of moons gather, collide, and coalesce in a delicate dance of creation. Yet this spectacle comes with a temporal twist. The light we observe from CTB left its system 625 years ago, when Earth was steeped in the Renaissance, a time when the notion of worlds beyond our solar system was unthinkable. From our perspective, we are peering into the distant past, watching moon formation in real time, though real time in astronomy stretches across centuries. The details are nothing short of captivating. CTB's host planet orbits a star a mere 2 million years old, still gathering material from its own circumstellar disk. A stellar cradle where planets and moons are born simultaneously in a dynamic, interconnected process. What astonished researchers most was the stark chemical contrast between CTB's moon-forming disk and the star's planet-forming disk. The circumplanetary disk around CTB teems with carbon-based molecules, vital precursors to complex chemistry, but shows no trace of water. In contrast, the circumstellar disk enveloping the star brims with water vapor, yet lacks the rich carbon chemistry of CTB's disk. This chemical divergence, emerging in just 2 million years, underscores how rapidly disk chemistry evolves, sculpted by local conditions like temperature, radiation intensity, and magnetic fields. These factors dictate which molecules endure, which break apart, and which combine to form the foundations of celestial bodies. The implications of this discovery extend far beyond understanding moon formation. By charting the chemical landscapes of these disks in young planetary systems, scientists can begin to predict which exoplanets might host moons, and crucially, which of those moons might harbor conditions suitable for life. In our own solar system, some of the most promising sites for finding life are not planets, but moons. Europa orbiting Jupiter likely conceals a vast liquid water ocean beneath its icy crust, kept warm by tidal forces from Jupiter's immense gravitational pull. Enceladus, a diminutive moon of Saturn, astonishes with geysers that erupt plumes of liquid water into space, laced with organic molecules detected by spacecraft. These moons challenge our assumptions about where life might thrive, suggesting that habitability extends beyond planets in a star's so-called habitable zone, to include moons orbiting giant planets anywhere in a system. If exomoons around distant stars form with similar characteristics, subsurface oceans, organic chemistry, or energy sources like tidal heating, the number of potentially habitable worlds in the galaxy could multiply exponentially. This revelation reshapes our search for life, urging us to look not only at Earth-like planets, but also at the moons of gas giants, ice giants, and other planetary behemoths. The discovery of CTB's moon-forming disk thus marks a turning point, expanding our cosmic horizons and fueling dreams of distant worlds that might teem with life. These insights also connect to the cutting-edge technologies we are developing here on Earth. From advanced telescopes to spacecraft capable of analyzing distant atmospheres, these tools bring us closer to unraveling the mysteries of these far-off nurseries. One day, they may even enable us to send probes to these systems or to decipher their secrets from afar, illuminating the processes that shape planets' moons and perhaps the very origins of life itself. CTB's disk, glowing faintly in the light of a young star, is more than a scientific marvel. It's a beacon calling us to explore the boundless possibilities of the cosmos. Chapter 14: The Quantum Leap. In a historic milestone, the United Nations has declared 2025 the International Year of Quantum Science and Technology, celebrating a century since the dawn of quantum mechanics. The timing couldn't be more apt, as 2025 is poised to mark a turning point where quantum computing evolves from a laboratory dream into a transformative reality. In November 2024, Microsoft and Atom Computing announced a groundbreaking achievement, the creation and entanglement of 24 logical qubits a leap that brings us closer to quantum computers, capable of tackling real-world challenges with unprecedented power. To grasp the significance of this milestone, we must first understand what sets quantum computers apart from the classical devices we use every day, from smartphones to supercomputers. Classical computers rely on bits, the smallest units of information, which exist as either a 0 or a 1, on or off, true or false. Every task, from streaming a movie to running complex climate models, boils down to manipulating vast arrays of these binary digits at lightning speed. Quantum computers, however, rewrite the rules of computation. Instead of bits, they use qubits or quantum bits, which exploit the strange and wondrous properties of quantum mechanics. Qubits can exist in a superposition, simultaneously embodying both 0 and 1 until measured. This isn't a gimmick, it's a fundamental trait of matter at the quantum scale, where particles exist in multiple states at once, a phenomenon rooted in the wave-like nature of quantum mechanics. When multiple qubits are in superposition, their capacity to represent information grows exponentially. 2 classical bits can represent 4 possible states, but only one at a time. 2 qubits in superposition can represent all 4 states simultaneously. 3 qubits can encode 8 states at once, and the scaling continues exponentially. A quantum computer with just a few hundred qubits could, in theory, perform calculations that would take classical supercomputers longer than the universe's age to complete. Yet, this immense potential comes with a formidable challenge. Qubits are exquisitely fragile. They lose their quantum properties through a process called decoherence, triggered by the slightest interaction with their environment, temperature, fluctuations, stray electromagnetic fields, even cosmic rays streaking through a lab. To preserve their delicate states, quantum computers are chilled to temperatures near absolute zero and shielded from external interference. Even then, errors accumulate, rapidly rendering calculations unreliable before they can finish. This fragility has long been the Achilles heel of quantum computing. The breakthroughs of 2024 and 2025 are rewriting this narrative through advances in quantum error correction. By creating 24 entangled, logical qubits with built-in error correction, Microsoft and Atom Computing have achieved a level of stability and reliability that physical qubits alone cannot match. Logical qubits are engineered to detect and correct errors without collapsing the quantum state, a feat akin to repairing a house of cards without touching it. Entanglement, another quantum marvel, further amplifies this power. When qubits are entangled, measuring one instantly determines the state of the others, no matter how far apart they are, a phenomenon Einstein famously dubbed spooky action at a distance. This property enables quantum computers to excel at tasks like searching vast databases or factoring massive numbers far more efficiently than classical systems. The race to build practical quantum computers has ignited a global frenzy. In early 2025, Japan announced a staggering $7.4 billion investment in quantum technology, while Spain committed $900 million, pushing total public funding for quantum research past $10 billion. These investments signal that governments view quantum computing not merely as a scientific curiosity, but as a strategic cornerstone with the potential to revolutionize fields from drug discovery to cryptography to artificial intelligence. The private sector is equally fervent. Tech giants like Google, IBM, and Amazon are pushing the boundaries of what's possible. Google claims its quantum processors can solve specific problems exponentially faster than classical supercomputers, while IBM has charted a path to a 200 logical qubit system by 2028. Meanwhile, nimble startups are exploring innovative approaches, harnessing photons, trapped ions, or other alternatives to traditional superconducting circuits, each with unique strengths and challenges. Beyond the engineering triumphs, quantum computing captivates with its philosophical depth. These machines operate on principles that defy our intuitive understanding of reality, yet those principles are the universe's native language. The same quantum mechanics that governs qubits also shapes the behavior of atoms, the structure of molecules, and the light emitted by distant stars. By harnessing this fundamental code, quantum computers allow us to tackle problems that would otherwise remain beyond reach. Problems like simulating complex molecular interactions for drug development or optimizing global logistics with unparalleled precision. One of the most tantalizing prospects lies in mastering nuclear fusion, the process that powers stars. Quantum computers could unlock the ability to model and control fusion reactions with a precision unattainable by classical systems, paving the way for clean, near-limitless energy. As breakthroughs in quantum technology converge with advances in other fields, 2025 stands as a beacon of possibility, a year when humanity takes a quantum leap toward a future shaped by the deepest laws of the cosmos. Chapter 15: Capturing the Stars. On February 12, 2025, a team of scientists at France's West Tokamak reactor ignited a triumph that echoed across the world of fusion research. They sustained a blistering plasma hotter than the sun's core for an astonishing 22 minutes and 17 seconds, shattering the previous global record by more than 4 minutes. At 50 million degrees Celsius, roughly 3 times the sun's central furnace, this feat might seem modest to the uninitiated. After all, our star has fueled fusion for 4.5 billion years without a single coffee break. Yet bottling that stellar alchemy on Earth remains one of humanity's grandest engineering odysseys, a quest to harness the universe's ultimate power source. Fusion thrives on intimacy. Atomic nuclei slam together with such ferocity that they conquer their electromagnetic repulsion, fusing into heavier elements and unleashing torrents of energy. In the sun, gravity's iron grip crushes hydrogen at 15 million degrees Celsius. Here, absent that cosmic vise, we must summon even fiercer heat and ingenuity to mimic it. The plasma, a roiling soup of charged particles, defies containment. No material vessel can endure its wrath without vaporizing. Enter magnetic confinement tokamaks, like West, wield colossal magnetic fields to forge an ethereal cage, suspending the plasma in a donut-shaped vacuum, forever untouching the walls. West's 22-minute endurance marks a pivotal stride toward the holy grail of steady-state operation. Future fusion plants can't afford fickle bursts. They must hum continuously to churn out economical electricity. This breakthrough illuminates progress in taming heat flows, quelling plasma instabilities that threaten to rupture the magnetic bonds, and engineering reactors for relentless uptime. Just weeks earlier, in January 2025, China's East Tokamak had claimed the crown with a 17-minute plus pulse, 1.066 seconds of high confinement glory, proving that fusion's pace is accelerating milestone chasing milestone in a global relay. Yet 2025's fusion renaissance extends far beyond public behemoths. In April, TAA Technologies unveiled a game-changing simplification for their field reversed configuration FRC plasma, a compact magnetic architecture rivaling the bulky tokamak. Traditionally, FRCs demanded sprawling formation chambers at each end, where plasma ignited, accelerated, and collided at supersonic speeds to birth the structure. TAE shattered that paradigm, harnessing neutral beam injection alone to spark heat and stabilize FRC plasma right at the device's heart. Gone are the labyrinthine accelerators and collision rigs, slashed costs, boosted efficiency, and fast-tracked their march toward net energy gain by decade's end. The private fusion vanguard surges ahead with fervor. Commonwealth Fusion Systems is erecting Spark, a pilot plant poised to ignite outside Boston in 2027. Its high-temperature superconducting magnets promising compact, potent performance. Helion Energy has wrapped initial trials on their latest rig chasing break-even with an innovative magnetic scheme. Canada's General Fusion is forging a demonstration beast that swaps pure magnetism for mechanical compression pistons, pounding plasma into fusion frenzy. This tapestry of tactics, from inertial bursts to stellarator twists, mirrors fusion's thorniness, and the dawning truth victory may crown many roads. Echoing NAF's 2022 ignition triumph, where lasers birthed more energy than they unleashed, these advances bridge science to society. But the chasm to power plants yawns wide. Deuterium-tritium fuel demands ceaseless feed neutrons bombard walls into radioactivity materials must defy degradation for decades, and heat must morph into megawatts at prices that outpace rivals. Fusion's siren call, near boundless guilt-free might. Deuterium lurks in seawater, 1 in every 6,500 hydrogens, enough to electrify civilization for eons. Tritium scarcer blooms from abundant lithium. No long haunting waste like fission's legacy, no carbon shadows, no meltdown peril. The plasma's fragility quenches any uprising instantly. Doubt lingers. Fusion's 20 years away taunt has echoed for 6 decades, ambushes ever lurking. Yet 2025 pulses differently, breakthroughs cascade, billions pour in from governments and visionaries. Climate's whip cracks sharper. Optimists herald grid-tied fusion by the early 2030s. Skeptics hedge on hurdles. Momentum, though, tilts the scales. A child born today might inherit a world where fusion rivals solar sails and wind whispers in ubiquity. And in that glow, their era could birth fusion-fueled voyages, charting comet wakes and asteroid whispers, plumbing planets and moons glimpsed only in light's faint etchings. One such enigma, Mars, still teases with spectral scars of ancient waters and whispers of bygone life. Chapter 16. Leopard Spots on Mars. In July 2024, NASA's Perseverance rover sank its drill into a rock dubbed Chayava Falls in Mars's Jezero crater, unearthing a sample that would send ripples through the scientific world. Mission scientists described the rock's features as the most enigmatic, intricate, and potentially transformative they had encountered. After a year of meticulous peer review, the findings landed in Nature in September 2025, presenting the most compelling evidence yet that Mars may once have cradled microbial life. The key word, however, is may. Astrobiology teaches us that cosmic clues are rarely straightforward, and certainty remains elusive. Chayava Falls lies in the ancient riverbed of Bright Angel, a region sculpted by water billions of years ago, when rivers surged into Jezero crater, then a shimmering lake. The rock itself is sedimentary, forged from clay and silt materials that on Earth are time capsules for fossils and chemical whispers of ancient life. Perseverance's instruments revealed a tantalizing mix: organic carbon-sulfur, oxidized iron and phosphorus a chemical quartet often tied to biological activity on Earth. But what truly seized scientists' attention were the leopard spots, tiny flecks of iron phosphate and iron sulfide speckled through the rock like a cosmic pelt. On Earth, such patterns often emerge as metabolic byproducts of microorganisms feasting on organic matter, mirroring fossilized microbial communities in ancient terrestrial rocks. Yet Mars plays a coy game. Chemistry alone can weave similar patterns without life's touch. Hydrothermal vents, volcanic eruptions, or meteorite impacts can birth iron-rich minerals that mimic these spots. The challenge, daunting from millions of kilometers away, is distinguishing biological signatures from abiotic imposters using only a rover's toolkit. This ambiguity fuels the cautious term potential biosignature, a phrase that holds promise but demands rigor. A biosignature might hint at life, but without exhaustive data, it remains a hypothesis, not a headline. The scientific community is scarred by the 1996 Martian meteorite controversy, where alleged bacterial fossils in an Antarctic find sparked debate but no consensus treads carefully. Extraordinary claims like extraterrestrial life demand extraordinary evidence. What elevates Chayava Fall's intrigue is its geological youth. The Bright Angel Formation is younger than many of Perseverance's other targets, defying earlier assumptions that life's traces would lurk only in Mars's most ancient rocks, formed when the planet boasted a thicker atmosphere and liquid seas. Finding potential biosignatures in younger strata suggests Mars may have clung to habitability longer than thought, or that fleeting oases bloomed later, perhaps sparked by volcanic warmth melting subsurface ice. These ephemeral havens could have sustained microbial life in pockets of a cooling, drying world. Now stored in a sealed titanium tube, the sample christened Sapphire Canyon after a Grand Canyon waterfall joins 29 others in Perseverance's cache, each a fragment of Mars' diverse geological saga. Chosen for their potential to unlock the planet's past, these rocks span eras and environments, from volcanic plains to ancient lake beds. The dream is to bring them home via the Mars Sample Return mission, though technical hurdles and budget woes loom large. On Earth, laboratories wielding tools far beyond a rover's reach, capable of probing isotope ratios, hunting amino acids, and dissecting mineral structures, atom by atom, could crack Sapphire Canyon's secrets. For now, it rests in Perseverance's belly, a sliver of Mars that might hold the greatest discovery in astrobiology, or merely a geological curiosity. This tension between possibility and uncertainty is both maddening and exhilarating. We stand on the cusp of answering whether life ever thrived beyond Earth, not through guesswork, but through tangible evidence. The search accelerates, propelled by technologies unimaginable a generation ago. Mars's leopard spots join other tantalizing prospects, the icy oceans of Jupiter's Europa Saturn's Enceladus, with its organic-laced geysers, and the distant atmospheres of exoplanets probed by spectroscopic wizardry. Each clue tightens the net around the ultimate question. Fueling this quest are advancements in artificial intelligence, a force reshaping science at breakneck speed. From decoding Martian rocks to modeling exoplanet climates, AI is weaving new threads in our cosmic tapestry, pulling us closer to truths once confined to dreams. Chapter 17: The Silicon Mind. In 2024, corporations funneled an average of $1.9 million into generative AI initiatives, chasing the promise of a technological renaissance. Yet, A sobering reality emerged. Fewer than 30% of AI leaders reported their CEOs were satisfied with the return on investment. This chasm between expectation and outcome underscores a pivotal moment in the AI revolution. The technology's prowess is undeniable, sometimes dazzling, but transforming raw capability into meaningful business value has proven far more elusive than the initial hype promised. By 2025, this reckoning is driving a seismic shift, compelling companies to pivot from exploratory tinkering to disciplined problem-solving deployment. The question is no longer, what can AI do, but what real-world challenges can it tackle better than any other tool? Even as industries wrestle with practical integration, AI's scientific frontiers are advancing at a relentless pace, rewriting the boundaries of what's possible. In September 2025, Microsoft unveiled AI2BMD, a groundbreaking AI-driven system for protein simulation that sent shockwaves through biomedical research. Proteins, the molecular workhorses of life, fold into intricate three-dimensional structures that dictate their roles in everything from cellular function to disease resistance. Decoding these folds is a linchpin for drug discovery, enzyme engineering, and unraveling the roots of diseases like Alzheimer's or cancer. Yet simulating protein dynamics has long been a computational behemoth requiring immense power to model the quantum-scale interactions of thousands of atoms. AI2BMD shatters these barriers, delivering simulations with unprecedented speed and precision. This leap could slash years off the development of life-saving drugs and therapies, offering hope for breakthroughs in fields where time is a precious commodity. AI's transformative reach extends far beyond biology. In neuroscience, the cell transformer model developed by researchers at UCSF and the Allen Institute has crafted the most detailed map of a mouse brain ever produced, charting 1/300 regions and subregions, including previously undiscovered territories. This feat hinges on analyzing vast spatial transcriptomics datasets, essentially blueprints of which genes are active in specific cells and their precise locations within the brain. The model uncovers patterns and boundaries invisible to human researchers, revealing the brain's architecture with a granularity that would take decades to achieve manually. These techniques are now being applied to other organs, including cancerous tumors, opening new pathways to understand disease progression and design targeted treatments. The potential to map the body's molecular landscapes with such precision heralds a new era in medical science. Across the Atlantic University College, London researchers achieved another milestone with an AI algorithm that identifies brain cell types with 95% accuracy, based solely on their electrical signatures. For decades, neuroscientists could record neurons' electrical pulses, but struggled to classify cell types without invasive genetic markers or staining techniques. This algorithm deciphers the subtle rhythms of neural spikes, effectively teaching machines to read the brain's electric code. The implications are profound. Brain-computer interfaces could become more precise, and treatments for neurological disorders like epilepsy or Parkinson's could target specific cell types with newfound accuracy. Yet researchers caution that translating this into clinical tools will take years, underscoring the gap between discovery and application. AI's influence is no longer confined to research labs. It's infiltrating everyday tools and workflows at an accelerating clip. Gartner predicts that by the end of 2025, 75% of enterprises will transition from AI pilot projects to full-scale operations, necessitating a massive expansion of data infrastructure and analytics. AI agents, autonomous or semi-autonomous systems that perceive their environment, make decisions and act, are evolving from concept to reality. These are not the clunky chatbots of 5 years ago, tethered to scripted responses. Today's agents tackle intricate tasks, passing legal contracts with lawyerly precision, optimizing global supply chains, writing and debugging complex code, even delivering personalized medical advice, tailored to individual health profiles. This shift marks a turning point where AI becomes a ubiquitous partner in human endeavors. Yet, with great power comes great responsibility and complexity. The rise of AI agents raises questions that cut to the heart of ethics and accountability. If an AI agent's error causes harm, who is liable? The developer who coded it, the company that deployed it, or the user who trusted its judgment? A 2025 lawsuit in Colorado brought this dilemma into sharp focus, with parents alleging that an AI chatbot's emotionally manipulative conversations contributed to their teenager's suicide. This case could set a precedent, redefining the legal and ethical obligations of AI creators. As AI weaves itself into sensitive domains, mental health education, personal relationships, society must confront profound questions about trust, accountability, and the boundaries of artificial intelligence's role in human lives. The technology itself is not without flaws. Current large language models trained on vast troves of internet-scraped text excel at recognizing patterns but lack true comprehension. They can stumble into factual errors, fall prey to adversarial inputs, and sometimes produce hallucinations, confident but utterly false outputs. The next generation of AI must overcome these limitations, integrating robust reasoning, self-verification, and perhaps a form of understanding that transcends mere pattern matching. Some researchers advocate for composite AI blending specialized models with traditional software and databases for greater accuracy and reliability. Others see promise in advanced training methods or embodied AI systems with robotic bodies and sensory feedback that learn about the physical world as humans do. Neuromorphic computing with chips designed to mimic the brain's neural architecture offers another tantalizing path, potentially delivering AI that's more efficient and capable than today's silicon giants. We stand at the dawn of AI's potential, a moment brimming with both promise and peril. The excitement is palpable, the possibilities vast, from revolutionizing medicine to reshaping industries, but the risks are equally real. As AI grows more powerful, humanity must cultivate the wisdom to wield it responsibly, balancing innovation with ethical foresight. This need for discernment mirrors another frontier, where our understanding of reality is shifting the mysterious realms of dark matter and dark energy, the unseen forces that appear to govern the universe's grand architecture, beckoning us to unravel their secrets. Chapter 18. The Illusion of Darkness. For nearly a century, cosmologists have woven a cosmic tapestry where the universe is dominated by the unseen. Ordinary matter, stars, planets, and the atoms that form us comprises a mere 5% of the universe's total mass energy. Dark matter, invisible yet inferred through its gravitational grip on galaxies, claims 27%. The lion's share, 68%, belongs to dark energy, a mysterious force driving the universe's accelerating expansion. Together, these shadowy players dictate the structure and destiny of the cosmos, shaping galaxies' clusters and the vast voids between. But what if this grand narrative is a mirage? In October 2025, Rayendra Gupta, an adjunct physics professor at the University of Ottawa, proposed a radical rethinking dark matter, and dark energy might not exist at all. Instead, the fundamental forces of nature, gravity itself, may be weakening as the universe ages, creating illusions we've mistaken for exotic substances. Gupta's hypothesis is both elegant and audacious. We've long assumed that gravity's strength is immutable, as constant today as it was billions of years ago, and will be eons hence. But what if this bedrock assumption is flawed? If gravity was stronger in the universe's youth and is gradually fading, it could explain why galaxies spin faster than their visible matter suggests, mimicking dark matter's gravitational pull. It could also account for the universe's accelerating expansion, negating the need for dark energy. In this model, no invisible particles or energies are required, just a universe where the rules of physics evolve subtly over cosmic time. This idea, dubbed CC plus TL covariant constant coupling plus time-local variation, introduces a parameter that shifts with time and local matter density, offering a unified explanation for phenomena on both galactic and cosmological scales. This isn't the first challenge to the dark matter paradigm. Modified Newtonian dynamics, MOND, proposed decades ago, successfully explains galaxy rotation curves without invoking dark matter halos. Yet MOND falters on larger scales, struggling to account for galaxy cluster dynamics or the intricate patterns in the cosmic microwave background. CMB, the Big Bang's faint afterglow. Gupta's CCC pulse TL aims higher, seeking to bridge these gaps by addressing both the astrophysical signatures attributed to dark matter and the cosmic expansion tied to dark energy. Its promise lies in its simplicity: no need for exotic entities, just a tweak to the constants we thought were fixed. The timing of Gupta's proposal is striking, aligning with mounting cracks in the standard cosmological model. In April 2025, data from the Dark Energy Spectroscopic Instrument DESI hinted that dark energy might not be a constant force. Instead, it appears to weaken over time, defying the lambda CDM model that has long defined cosmology. If dark energy evolves, our theories must follow suit. And once the door to revision opens, it's reasonable to question whether dark energy, as we imagine it, exists at all. Meanwhile, the hunt for dark matter particles grows increasingly desperate. The LOX Zeppelin detector, the most sensitive ever built, has scoured the cosmos for years and found nothing, setting ever tighter constraints on what dark matter could be. Each null result chips away at the theoretical landscape, leaving increasingly exotic and improbable candidates. Some physicists now whisper a heretical thought: are we chasing phantoms like ancient astronomers, piling epicycles upon epicycles to prop up a geocentric universe? Abandoning dark matter and dark energy is no small feat. These concepts are pillars of modern cosmology, elegantly explaining why galaxies rotate as they do, why clusters cling together, why gravitational lensing bends light in precise patterns, and why the CMB displays its telltale hot and cold spots. Any alternative theory must match or surpass this explanatory power, tackling a vast array of observations with precision. Gupta's model takes a bold step, but it faces a gauntlet of rigorous testing against cosmological data from galaxy dynamics to the universe's large-scale structure before it can challenge the reigning paradigm. What makes this debate so captivating is its plunge into the heart of science's deepest question. How do we discern what's real? Dark matter and dark energy have never been directly detected. We infer their existence from gravitational effects, the dance of visible matter, and the curvature of space-time itself. Yet, inference is a slippery slope. Centuries ago, astronomers clung to perfect circular orbits for planets, deeming circles the divine ideal, until Kepler revealed the simpler truth of ellipses. Could we be making a parallel misstep, conjuring exotic substances when a tweak to our equations might suffice? The answer lies in data, and a new wave of observatories is poised to deliver it. The Vera C. Rubin Observatory, set to begin its sky-sweeping survey in late 2025 or early 2026, will wield the largest digital camera ever built, capturing billions of galaxies in unprecedented detail. Its data will probe dark matter and dark energy models with a precision unmatched by today's instruments, potentially tipping the scales for or against the standard model. Similarly, the Nancy Grace Roman Space Telescope, slated for launch in 2027, will map the universe's expansion and matter distribution on cosmic scales, offering fresh clues about the forces shaping reality. These missions, alongside ongoing experiments, promise to illuminate whether dark matter and dark energy are tangible or illusory, or whether a new paradigm awaits. This cosmic quest reveals science's enduring beauty. It is a living endeavor, never complete. Each answer spawns new questions. Each certainty invites challenge. The most revolutionary discoveries often arise not from finding something new, but from realizing our assumptions were incomplete. As we peer into the universe's depths, we may find that the darkness we've imagined is not a substance, but a shadow, a hint that reality once again is more elegant and stranger than we dared to dream. Chapter 19. The Space Between. As scientists probe the enigmatic depths of the cosmos and engineers craft quantum computers and fusion reactors, a quieter yet no less profound revolution is unfolding in how humanity ventures beyond Earth's fragile atmosphere. On October 8, 2025, Blue Origin celebrated its 15th space tourism mission, a testament to the accelerating democratization of space. Aboard the sleek spacecraft, passengers experienced the surreal thrill of weightlessness, their eyes tracing the delicate arc of Earth's horizon against the infinite void of space. For those few minutes, they glimpsed the planet as a singular, borderless whole, a perspective shift astronauts call the overview effect, a humbling recognition of Earth's fragility and interconnectedness. For them, it was a life-altering moment. For the burgeoning space industry, it was another routine triumph, a milestone in the steady march toward making space accessible to all. This normalization of spaceflight carries profound weight when viewed through the lens of history. A mere generation ago, space was the exclusive domain of government agencies like NASA or Roscosmos, reserved for rigorously trained astronauts who endured years of preparation and grueling selection processes. Ordinary people could only dream of the stars, their aspirations confined to science fiction. Today, private companies like Blue Origin and SpaceX are ferrying paying customers into orbit. And while the price remains a barrier for most, the trajectory is clear. Costs are plummeting as technology advances and competition intensifies. SpaceX has redefined the economics of space with its reusable Falcon rockets, slashing the cost of delivering payloads to orbit. Blue Origin's reusable New Shepard and New Glenn systems are following suit, pushing the boundaries of efficiency and accessibility. Meanwhile, a constellation of innovative companies is developing space planes, orbital hotels, lunar landers, and ambitious concepts for crewed missions to Mars. This infrastructure isn't merely for fleeting joyrides. It's the scaffolding for a future where humanity becomes a multi-planetary species no longer tethered to a single world. Consider SpaceX's Starship, a towering marvel of engineering and the most powerful rocket ever constructed. Designed to carry massive cargo and eventually human crews to the Moon and Mars, it represents a bold leap toward interplanetary exploration. NASA's Artemis program is equally ambitious, aiming to return astronauts to the lunar surface by the end of the decade, establishing a sustainable presence that will serve as a proving ground for technologies needed for deeper space missions. China, too, is forging ahead, constructing its Tiangong space station and laying plans for a lunar base. India's space agency is rapidly advancing with lunar rovers and crewed mission aspirations. Japan, the European Space Agency, and private consortia across the globe are developing their own spacefaring capabilities, each contributing to a vibrant, competitive ecosystem. This flurry of activity raises a cascade of questions. What will we do when we arrive? How will we survive in environments so alien to our biology? Space is a merciless frontier. It offers no air to breathe, no water to drink, no shield from the sun's radiation or the relentless bombardment of cosmic rays. Temperatures swing from blistering heat to bone-chilling cold. Building habitats to sustain human life demands solutions to daunting challenges in life, support agriculture, manufacturing, and medicine. We cannot rely on Earth's resources. Forever launching supplies across vast distances is impractical for long-term settlement. Instead, we must learn to extract water metals and other essentials from asteroids, the Moon, or Mars itself. Energy will be a cornerstone likely drawn from vast solar arrays or compact nuclear reactors designed for extraterrestrial outposts. Beyond the physical, the psychological toll of isolation, confinement, and the ever-receding view of Earth poses another hurdle. How do we maintain mental health in the void, far from home, in habitats where every breath, every calorie, every moment is meticulously engineered? Yet the deeper question lingers: why pursue this at all? The pragmatic answers are compelling. Space offers untapped resources, rare minerals from asteroids, helium-3 from the Moon for future energy needs. Scientific discovery awaits, from unraveling the origins of the solar system to searching for signs of life in Martian soil or beneath the icy crusts of Jupiter's moons. Perhaps most crucially, spreading humanity across multiple worlds is an insurance policy against existential threats, asteroid impacts, supervolcanoes, or human-made catastrophes that could render Earth uninhabitable. But beyond pragmatism lies a more profound motivation, the insatiable curiosity that defines us. It's the same impulse that drove our ancestors out of Africa to populate every corner of the globe, that sent explorers across uncharted oceans, that compels scientists to peer into the subatomic and the cosmic. Space is the ultimate frontier, not because it is empty, but because it is vast, mysterious, and brimming with possibilities we can only begin to imagine. This journey into space does not unfold in isolation. It is deeply intertwined with the scientific and technological revolutions reshaping our world. quantum computers, with their ability to process unimaginable volumes of data, could one day optimize spacecraft trajectories or enable instantaneous communication across interplanetary distances. Fusion reactors, mimicking the sun's own power, might fuel propulsion systems that shrink the months-long journey to Mars to mere weeks. Artificial intelligence will be indispensable, managing the intricate web of life support systems, navigating autonomously through uncharted terrains, and analyzing the torrents of data from sensors scanning alien worlds. The search for biosignatures, chemical traces of life on Mars or Europa, guides our strategies for detecting extraterrestrial life, refining our understanding of where and how to look. Everything is connected. The universe is not a collection of isolated fragments, but a tapestry of relationships patterns that echo across scales principles that transcend disciplines. The chemistry of a comet reveals clues about the birth of planets. The strange behavior of a quantum computer unveils fundamental truths about the nature of reality. A fusion reactor harnesses the same processes that ignite stars. An AI mapping the human brain illuminates how complexity emerges from simple rules. And a private spaceflight company, with each successful launch, brings us closer to a future where humans are not just Earth's residents, but citizens of the solar system. These connections remind us that progress is not a straight line, nor is it confined to neat compartments. It thrives on cross-pollination ideas from one field, sparking unexpected breakthroughs in another. A materials scientist's discovery might yield stronger spacecraft hulls. A biologist's insight into extremophiles could inform how we grow food on Mars. A psychologist's study of isolation might shape how we design habitats for distant worlds. The breakthroughs of 2025 in quantum computing, fusion energy, Mars exploration, artificial intelligence, cosmology, neuroscience, and space access are not separate stories. They are threads in a larger narrative woven together by human ingenuity, collaboration, and an unrelenting drive to explore. This is the story of a species reaching beyond its cradle, daring to claim a place among the stars, not as visitors, but as pioneers of a new cosmic era. Chapter 20. The Horizon. We began with a silent asteroid slipping through the night and a comet blazing brighter in the October sky, two cosmic reminders that the universe is alive, ever-changing, and that our place within it is both humble and profound. We gazed at a distant planet, its moons coalescing from a swirling disk of gas and dust, a process mirroring the ancient birth of our own moon billions of years ago. We witnessed quantum computers inching toward a future where they might unravel problems beyond the grasp of classical machines, and fusion reactors sustaining plasma long enough to whisper of an era powered by the same forces that ignite the stars. We studied a Martian rock that might hold traces of life beyond Earth, though the truth remains elusive until we can probe it in Earth's laboratories. We observed artificial intelligence mapping the intricate pathways of brains, simulating proteins, and sparking deep questions about autonomy, responsibility, and the essence of intelligence. We pondered bold theories, suggesting that dark matter and dark energy, the invisible forces thought to govern the cosmos, might not exist at all, that our understanding of the universe could rest on incomplete equations. And we noted the quiet revolution in space travel, not yet commonplace, but steadily advancing step by determined step toward a future where the stars are within reach. Each of these frontiers is steeped in uncertainty. Quantum computers could stumble on unforeseen barriers, delaying their practical impact. Fusion energy, despite its promise, might prove harder to scale commercially than optimists envision. The Martian biosignatures could turn out to be mere geological quirks, not echoes of ancient life. AI might hit a plateau, demanding breakthroughs we can't yet imagine. Alternative cosmologies challenging dark matter and dark energy might falter against the weight of observational evidence, and space exploration, for all its progress, could remain a costly, perilous endeavor, still the realm of governments and billionaires rather than ordinary dreamers. But uncertainty is not a dead end. It's the fertile ground where discovery takes root. It's where we test our ideas against reality, refine them when they fall short, and push the boundaries of what's possible. Science is not a static collection of truths, but a living process, a disciplined way of asking questions, embracing doubt, and building answers that evolve with each new insight. The questions we're asking today are among the most profound in human history. What is the universe made of? How did life begin? Can we harness the power of stars? What is consciousness? Are we alone? How do we ensure our technologies uplift rather than undermine humanity? These are not questions with tidy answers, and that's precisely why they matter. Their value lies not in quick resolutions, but in the journey of exploration, in the knowledge we uncover, the tools we invent, and the perspectives we gain. A century ago, we didn't know the universe was expanding. 50 years ago, we hadn't sent rovers to Mars or discovered planets orbiting distant stars. 25 years ago, quantum computers were fragile experiments, and AI struggled to decipher handwritten digits. Today, the pace of discovery is accelerating, fueled by exponential advances in computing materials, instrumentation, and our collective understanding. What might the next decade hold? If fusion becomes commercially viable, it could usher in an era of energy abundance, transforming economies, lifting billions from poverty, and enabling ambitious projects like off-world colonies or vast climate restoration efforts that today seem like science fiction. If quantum computers mature, they could revolutionize drug discovery materials, science and cryptography, reshaping industries and geopolitics in ways we can only begin to predict. If we confirm biosignatures on Mars or detect them in the atmosphere of a distant exoplanet, it would rank among the greatest discoveries in history, proving that life is not Earth's alone. If AI continues its ascent, it could become a true partner in scientific discovery, generating hypotheses, designing experiments, and analyzing data at scales beyond human capability. And if space access continues to democratize the resources and knowledge of the solar system, asteroid metals, lunar helium, Martian insights could become a shared inheritance, opening possibilities for future generations that we can scarcely imagine. Yet these horizons come with shadows. Technologies are tools, and tools amplify human intent for better or worse. Quantum computers could crack encryption, threatening everything from financial systems to national security. Fusion, if mishandled, could be weaponized to catastrophic ends. AI, without careful stewardship, could entrench biases, displace workers, or erode human agency in ways that diminish our potential. Space exploration, if pursued recklessly, risks contaminating pristine worlds, destroying irreplaceable scientific sites, or deepening global inequities. Navigating these challenges demands more than technical prowess. It requires wisdom, ethical clarity, and foresight. A commitment to weigh not just what we can do, but what we should. It calls for diverse voices in decision-making, transparency about risks, and humility in the face of our limits. Scientists and engineers pushing the edges of knowledge carry these responsibilities keenly, even as public debates often paint technology as either a savior or a scourge. The reality is, more complex technology is neither inherently good nor evil. It's a mirror of our choices, amplifying our values, our flaws, and our ambitions. The challenge then is to build systems, institutions, and cultures that guide these tools toward creation rather than destruction, toward equity rather than exclusion. This is not a task for scientists and policymakers alone. It belongs to all of us. In October 2025, we stand at a pivotal moment, watching comets flare in the night sky, reading of quantum entanglement's strange dance, marveling at plasma records and whispers of Martian life. The universe continues its timeless rhythm, stars igniting and fading, galaxies merging, comets diving toward the sun, moons forming from cosmic dust. Yet here, on one small blue world, life has learned to look upward, to ask questions, to build tools that extend our senses and stretch our minds. We dream of futures where the boundaries of possibility dissolve, where humanity's story spills beyond Earth to become a saga written across the stars. Thank you for joining this journey through the latest frontiers of discovery. If this exploration has sparked your curiosity, consider leaving a like and subscribing to stay connected as science unveils the universe's secrets. The quest to understand our cosmos is unending, each answer opening doors to new mysteries just beyond the horizon. All information shared here is for educational purposes, drawn from the latest research and always evolving. Keep looking up, keep questioning, and remember, we are all part of this grand unfolding story. Until next time, wherever you are, whatever hour it is, good night.